Hi everybody, it's video notes 8.2. We're going to do rate calculations and Hess's law and dilutions. So here's the stuff in the book that you could look at. I recommend putting this in your notes for practice. So rate. What is rate? It's a measure of how much a chemical reaction changes over time. So when we say how much, we mean the amount of change over time. Okay. So change in amount over change in time. So one of the ways we can do amount is molarity, and one of the ways we can do time is minutes. You could also have milliliters per second. That's another rate, change in milliliters per change in second, and that's what we did in a lab, or we will do in a lab. How does rate compare to time? Faster rate means it takes less time. Okay. Lower rate means it takes longer time. More time. Okay, so they're they're inversely related. So here's some data from a chemical reaction. So here's how much time passed, and here's the concentration of one of the chemicals, S2O8 -2. Okay, that's an ion, so it's molarity. So we can do rate at any point in the reaction. So over here, they looked at the rate between 0 and 60 seconds. And so they use these two numbers. So you have to subtract the amount. So 0.4048 divided minus 0.042 over 0 minus 60. And so you're going to get a negative number. But what happens is you get 1/10 to the -4 moles per liter per second, which is molarity per second. So that's the rate at which, since this is negative, it means the S2O8 minus is disappearing. So that means it must be a reactant. So if you get a negative rate, that just means that you're looking at the reactant disappearing. If you get a positive rate, you're looking at a product forming. Okay, so you can do, that's an instantaneous rate over a 60-second interval. You could do a rate over the whole reaction, 300 seconds it took, or that's how long they were timing it for. So the overall rate would be, overall rates, you just have to do the end of the reaction. So, and you can do it either way. So 300 minus 0 seconds. And then you have 0.025 molarity minus 0.048 molarity. And what you get is 0.023 for 300 seconds, which divide out, don't leave it in fraction form, so it's negative. Negative 7.67 times 10 to the -5th molar over seconds. So this is the overall rate of disappearance of S2O8 -2 of that polyatomic ion. All right, so what the negative sign means is that that stuff is disappearing over time, so it's a reactant. If you ever get a positive rate, that means you're looking at formation of product over time. So rate is amount of change in amount over change in time. And you can do it for any time interval. We could have gone from here to here, or we can go from here to here. So any time interval, you just got to make sure your numbers on top correspond to, if I use this number, I got to use that number. Okay. Oh, look, it's more data about a rate. So here's the chemical reaction. All right. So what's going to happen to the N2O5? Well, it's going to collide with enough energy at the right angle to make NO2 and O2. And so if that's happening, here's the time. So look what happens to N2O5. Well, the amount decreases, the concentration decreases, which makes sense. And we start with 0 of these to start with, and then the amount of product increases. So we can do any rate for any of the substances. And so let's do N2O5 over this time interval. Okay. So then we got to use these numbers. So the molarity, change in molarity, is going to be equal to 0.0061 molar minus 0.0169 molar divided by 700 seconds minus 100 seconds. And so you get 1.8 times 10 to the fifth, -5th, molar per second disappearing. And it's going to be negative because you get a negative number. Subtract. So a big number minus a small number. So that's disappearing. That's the rate at which N2O5 is disappearing. And you can see for products, we can do rate of NO2 forming. So let's do that in the same time interval. So do this here with this again. Okay. So NO2 rate is going to be 0.0278 minus 0.0063 divided by the time interval, which was 700 seconds minus 100 seconds. So we find out that NO2 is appearing at a rate of 3.58 times 10 to the negative fifth molar per second. Okay, it says 3.58 times 10 to the negative fifth molar per second. We could do this with O2, but so you could do the rate of disappearance, the rate of appearance of that, the rate of appearance of that. You could do rate over any time interval for any reactant or any products. Okay. Now we get to talk again about enthalpy, which is our delta H. Last video, you saw to do bonds breaking and bonds forming and add that all together. We could do the rate, I'm sorry, not rates, the enthalpy of this reaction by using other reactions, delta H's, as long as those reactions add up to our target one. So this is what we're trying to do. So this is our target reaction. This is what we want to see the delta H of. And we have these two reactions that were given, right? So then what you want to do is you want to take these two reactions and manipulate them so that when you're done manipulating them, you can add them together and get this target reaction. So let's see what happens. We have this reaction, which has magnesium and a half oxygen mole making magnesium oxide with an enthalpy of negative 604 kilojoules per mole. We also have this reaction, copper oxide, 1 mole gives you 1 mole of copper and 1/2 mole of oxygen with a delta H of positive 155. So if we don't do anything to these reactions, don't change their delta H's at all, and we add them together, we can see that the 1/2 O2 will cancel out on both sides and leave us with Mg plus CuO, Mg plus CuO. It gives us, after the arrow, MgO plus Cu. So we get this target reaction, Mg plus CuO gives us Cu plus MgO, which is this reaction, if we add them together. So then all we have to do with the delta H's is add them together, and we get negative 449 kilojoules per mole. So this time we have this is our target reaction. This is our target. This is what we're trying to find the delta H of. So we need to take these two equations. Sometimes there could be 3 or 4 or 5 equations. Doesn't matter. What we want to do is manipulate these so that when they add together, they give us our target. So if I look here, I have C on the left and O2 on the left. That looks good because that's what happens here. And I get CO2 on the right. Over here, I get CO. So this CO2 is not part of what I want. Right? If I look at the second reaction of O2 on the left and CO on the left, but then it gives me 2 CO2 on the right. So since this target reaction has no carbon dioxide in it whatsoever, I'm going to have to make sure when I add these together that carbon dioxide cancels out. Right. All right, so what I would have to do with this reaction is flip it so that I have 2 CO2, arrow, O2 plus 2 CO. And if I do that, then the CO2 from this side will sort of cancel with the CO2 from that side. So this reaction is no longer there like that. But if I flipped it around, I have to then take this delta H and flip it. So instead of being negative 566, it's positive 566. Okay. So if I do something to a reaction, I got to do the same thing to the delta H. All right. This reaction now, if I added these together, I would still get a CO2 on this side because there's only one in each. But if I take this whole reaction and multiply it by 2, then I'll have 2 carbons moles, 2 oxygen moles, and 2 carbon dioxide moles. So then what I'd have to do with this delta H is also multiply it by 2. And so that's going to give me 393 393.5 times 2 is, and it's still negative because I didn't flip it around, is negative 787 kilojoules. Okay. What happens if I do all that? Well, let me add it up now. So now I have 2 C's on this side, and then plus 2 O2s on this side. That's from the first reaction. What about from the second reaction on the left side? I have 2 CO2s. So I have this, this, and this on the left. After the arrow, I have this, this, and this. So let's write out after there. 2 CO2s because of this coefficient, plus an O2, plus 2 carbon monoxide. All right, so if I look at this whole thing, that's these added together. What happens? Well, this 2 CO2s cancel each other. Goodbye. One of these goes away with that, and so I still have one left. I still have 2 C's. I forgot something. Flip that. Two C's. Oh, all right. Wait a second. Flip that. I get 2 C's. Which I want. That's perfect. 2 C's plus O2, 2 CO2, 2 COs. Look what happened. All right, and it took me a second to see what I had, but this is what I have overall. Guess what? Good news, peeps. This is that. All right. So how did I do that? Well, I added these together after I manipulated them. So I had to multiply the first equation by 2. So I had to multiply the delta H by 2. I had to take the second equation and flip it around the arrow. So I had to take the negative sign and flip it to be a positive sign. And then I added them together. So I have negative 787 plus 566 gives me a grand total of maybe 221 kilojoules for that reaction. Now, that's how you figure out the delta H using, it's called Hess's law. And you're given a series of equations, and you have to manipulate them to make your target equation. And I'm just going to erase some of this so we can see we're right, because I have an answer coming in a second. Let's see. Woohoo! Yay us. All right, so here's one that you can practice with. So here's your target, and here's 3 equations. This one's a little trickier because of the fraction, but I think you can figure it out. So you manipulate these 3 equations. You can multiply, you can divide, you can flip around the arrow, but whatever you do to this equation, you have to do the same thing to delta H. And once all of these equations add up to this, then you add up the H's. All right, now, last but not least, we got to talk about concentration and dilutions. So just to refresh your memory, if you have Kool-Aid, there's a solute and a solvent. So the powder and the sugar is a solute and water is a solvent. Tap water, there's ions in it, so tap water is the solvent. And rubbing alcohol, 98% rubbing alcohol, well, the solute is water because 2% is water and 98% is rubbing alcohol. So every solution has a solute and a solvent. And so one thing we can use to describe a solution is molarity. Molarity is concentration. And then we can talk about whether a solution is concentrated. That means there's a lot. Oh, look at all that solute in that solvent. Dilute means not a lot of solute and solvent. Okay. So you can take a solution you already have and make it dilute. So which one is more concentrated? Dark Kool-Aid or light Kool-Aid? More concentrated. All right. Higher concentration. All right. Higher concentration. Higher concentration of rust in the water. Higher concentration of SpongeBob. Dilute. 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 Dilute because you can't taste the rust. It's a little bit more diluted. 50%. Okay, so we have to remember molarity. Molarity is said it has a capital M as a unit, and it's moles of solute per liters of solution. And so something is 5 molar because there's a molar. Yay! All right. So just to refresh your memory, 25 grams of calcium fluoride. We want to know dissolved in 150 milliliters of water, what's the molarity? Well, we have to change grams into moles, so we have to go get grams from the periodic table. And when we go get them, we find out that it's 78.48. I got that from the periodic table of fluorine, 2 fluorines and a calcium. This is the periodic table. That's in 1 mole. So that gives me 0.32 moles of calcium fluoride. And then 150 milliliters equals 0.150 liters. You can divide by 1,000, divided by 0.150 liters, and we find out the molarity is 2.13 molar for this solution. Okay, so that's how solutions are made. You take a solid, you dissolve it in the water, and you can get its concentration, molarity, moles per liter. Now, if you have a concentration already, a solution already, you know its concentration. So if this was 1.0 molar, then what you're seeing is these number of moles in this number of liters. This is concentrated compared to the other one because it's got more particles and less volume. Okay, this is diluted. Right? So we still have the same number of particles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18 particles, but now we have twice as much volume, so it's diluted. So this would be 0.5 molar, so it's less. So diluted means the concentration goes down. But what changes is the amount of solution, the volume, not the amount of particles. So these, if this was this many moles, this is still the same number of moles, but it's in more volume. Okay, so the moles stay the same as you go, but the volume changes. So then the molarity changes because the volume increases. So we have to be able to make solutions from other solutions to see how concentration affects reaction rate. So we want to memorize this equation because when the molarity of 1 times the volume cancels out and you're left with moles, moles equal moles. We just have bigger volume. So higher concentration means less volume. Lower concentration means higher volume. So I always do my more concentrated as my 1s and my less concentrated as my 2s. And so let's practice what we can do with the equation. All right, so say we have a 4 molar solution. So we got this container on the shelf that says 4 molar MgSO4. And we want to get another solution that's diluted. So what do we have to do? Well, we have to take some of this, a little bit of this, a little bit of this, a little bit of this, and then put it in a container and then add water to dilute it. All right, now, how can we quantify that? Well, we have a 4 molar solution. We're going to use the equation M1V1 equals M2V2 is our dilution equation. So the molarity of the first solution, I always use it as my stock solution, is the higher concentration. When I'm done, I want it to be 1.7 molar. So I want it to be less concentrated. I don't know how much of this, little bit of this, to make this. So I don't know how much of the 4 molar to use, but I know when I'm done diluting it. So when I'm done diluting it, I want to have 300 milliliters, which is equal to 0.3 liters. Okay, just change it to liters because molarity means mole per liter. So then I set this up with my formula for dilution. M1V1 equals M2V2. Molarity times volume equals molarity times volume of the second one. So I have 4 molar times my x. That's what I'm trying to figure out. How much should I use? 1.7 molar times 0.3 liters. Now to solve for this x, I got to divide by the 4 molar. Goodbye. Divide by the 4 molar. Look at molarity cancels out. So my answer for x is going to be in liters. And I find out it's 0.1275 liters, which equals 127.5 milliliters. But what does that mean? It means I have to measure 127.5 milliliters of 4 molar solution into a new container. And then I take that, add enough distilled water. I'm going to put DI for distilled, deionized water, to make 300 milliliters of 1.7 molar solution. All right. So what does that mean? So here's me. Here's my graduated cylinder. Right, with the marks on it. I pour 127.5 milliliters of this. And then I take that, I'm taking it over here to a new container and pour it in. And then add water to this. And then, okay, so here's water. Water. And then when I'm done, I get 300 milliliters total. And then it's 1.7 molar. Okay? Look at that. Those are great drawings. I know they help. All right. So I want you, because Ava needs to make a 500 milliliters of 1.6 molar solution from a concentrated 6 molar stock solution. What should she do? So do the calculations and see if you can get a number. And then I want you to write a sentence. Write a sentence after you figure out this. Write a sentence describing what to do. Describing what to do based on the last example. Okay. All right. Oh, we'll do this one in class. So we'll practice that. Here's why. We're going to be doing that in class, and then we're going to be able to see the effect of concentration on reaction rate because we know how to dilute solutions. All right, so to review, Potato says know your formula for molarity. Molarity equals moles per liter. Know it. Know the dilution equation. Molarity of one solution times its volume. It's got to be equal to the molarity of the other solution times its volume. And I always use the ones for concentrated, twos for dilute. But that, as long as you keep them together. When you go to make a dilution, you don't add a specific amount of water. You just take the amount of the first one and then add water to it until you get the volume of your second one. Okay. So overall, kinetics looks at rates of reactions. Rates occur in steps, so the slowest step determines the rate. Rate is amount over time. You can calculate delta H by using a series of reactions that add to a final reaction, but whatever you do to the reactions, you got to do to their delta H's, and then add them when you're done. Dilution is a way to change the concentration of solutions. So you have to know how much of the solution should I use the concentrated one and how much should I dilute it to? How much water should how much should I add water to make it diluted? Okay. Please do self-check 10.6, page 267. Read all that stuff for backup. And here's what we learned. Peace out.